Welcome. Let's take a look at number 2. A toy manufacturer wanted to see how long, on average, a new toy captures children's attention. For a random sample of 7 children who played with the toy, the mean attention span was 27 minutes, with standard deviation 4 minutes. If we assume that attention spans are normally distributed, find a 90% confidence interval for the mean attention span of children playing with this new toy. All right, so let's start with our given values. So we have a random sample of 7 children. So we have our N, sample size 7. And the mean attention span for the 7 children was 27 minutes. So that's our sample mean, X bar. With standard deviation 4 minutes. All right, so here's where we have to be careful and always ask ourselves if the standard deviation given is for the entire population of children, or is it for the sample of children? And by reading the sentence, it is hopefully clear that it says it's for the sample of 7 children. This was the mean with this standard deviation. So that standard deviation was for those 7 children. So we could put the word sample standard deviation in front of it for more clarity, but it should be clear by the context of the sentence that this is sample standard deviation. So our symbol is S, sample standard deviation 4 minutes. All right, and then they'd like us to construct a 90% confidence interval for the true mean. So we're estimating mu, and we always ask ourselves, do we know sigma? So in this case, sigma population standard deviation is unknown, and that's why the interval that applies is the t-interval, which is based on the t-distribution. All right, and then we'll come to our calculator. So stat tests, we go to our t-interval. And now we don't have the original data on the 7 children. We just have the statistic X bar. So we want to go to stats as our input. And then sample mean 27, S4, sample size 7, 90% confident. All right, and I'm going to round to a whole number just to make it easier to demonstrate something coming up here in a moment. So let's do a whole number. So 24 would be our lower limit. And then less than the parameter we're estimating, mu. And then my upper limit there, 29.938 would round to a whole number 30. All right, so based on a sample of 7 children, we estimate with 90% confidence that the true mean attention span, or we could say population mean, either of those is fine. So for all children, so based on these 7, we are estimating that for all children that the mean is somewhere between 24 and 30 minutes. All right, so I'm going to graph that. So 24, my lower limit, 30, my upper limit. And I'm going to include my point estimate. So the sample mean would be in the center of that interval. So always just a reminder, vocabulary, that is our point estimate for mu. So X bar is our best point estimate for mu. And then I'd like to put down the margin of error in this confidence interval. So they believe that the mean best point estimate is 27, and then plus or minus. So I'm just going to come over here. The idea here is we could have written the confidence interval in the form. We believe the mean is 27. plus or minus, and then let's find our margin of error. All right, so there's different ways to find the margin of error. One is just to look at the distance from the center x bar to the lower or upper limit. And I would think that's probably the quickest way. 30 minus 27, that's a difference of 3 minutes. So that distance would also be 3. All right, I will just make a note here. The other way to find it would be to use the formula. If we know upper limit, lower limit, we can just find the difference and divide by 2. So 30 minus 24 divided by 2 is 6/2, or 3 minutes. So we could say we believe that the true mean for all children who play with the toy is 27 minutes, plus or minus 3 minutes. Okay, so let's see how this compares to the wording here on number 3. A toy manufacturer wants to see how long on average a new toy captures children's attention. They test 7 children selected at random and calculate the mean attention span of 27 minutes. Assume the population standard deviation is 4 minutes and that attention spans are normally distributed. And again, find a 90% confidence interval. All right, so as we're summarizing the values here, n is 7, so that didn't change. And the mean for those 7 children had a calculation of 27 minutes, so that's the same. Then the assume the population standard deviation is 4 minutes. So that is our sigma. So that's for the entire population. They're going to make that assumption. And we're still doing a 90% confidence interval. So the difference here, we're estimating a mean, and sigma is known to us. So when sigma is known, that's when we are able to use the ZInterval, which is based on the Z or standard normal distribution. All right, and we're going to see then how this affects our confidence interval. So back to stat tests. This time we're going to pick a ZInterval, enter our sigma, x bar, n, and confidence level, and calculate. And I'm going to round to a whole number again. So that lower limit would round to 25, less than mu, less than upper limit there would be 29. All right, so graphically here, now my lower limit, 25, upper limit, 29. The point estimate, x bar, still in the center of that distribution. So what's happening now is we still have a 90% confidence interval, but the margin of error is smaller. So essentially, because we know something about our population, it allows us to have confidence intervals that are more accurate, so smaller margin of error. So the quickest way to do this one here is just to say that distance again, 29 minus 27. Now we just have a 2-minute margin of error. And again, you could use the formula upper limit minus lower limit divide by 2 if you would like. Either way is totally fine. That will be 2. So in this case, we could say we think that the mean is 27 minutes plus or minus 2 minutes. All right, so as we read questions, estimating a mean, we're going to look for that information on sigma, whether it's known or not. So the last 2 questions here, rather than doing an entire confidence interval, we're just going to focus on reading the question and determining which interval would apply. All right, I call this my lobster question. All right, so number 1, a Maine lobster trapper wishes to estimate the mean weight of his catches. He recorded the weights of 6 randomly caught lobsters and calculated their mean weight to be 1.8 pounds. Assume lobster weights are normally distributed, and the population standard deviation is 0.6. When finding a 95% confidence interval for the population mean of his catches, does a Z-interval or T-interval apply? All right, so the given values, N is 6. And the mean was calculated for those 6 lobsters to be 1.8 pounds. And a note here, actually as above as well, it said that assume our variable lobster weights are normally distributed. So that's a requirement for Z or T when we have a sample size that's under 30, so small sample size. So that's why that is given to us. And then they give you, assume the population standard deviation is 0.6. All right, so again, we're estimating mu. We'll learn to estimate another parameter shortly, but estimating mu, sigma known to us, population standard deviation known, so that would be your Z-interval. All right, and then we'll compare that to number 2. So a Maine lobster trapper wishes to estimate the mean weight of his catches. He records the weights of 6 randomly caught lobsters and calculated their mean weight to be 1.8 pounds. The standard deviation was 0.6 pounds. So now that standard deviation was for those 6 lobsters. So again, just by the context here, reading the question, it doesn't say assume this is true for all lobsters. It says, and past tense there kind of indicates this as well, for the 6 lobsters, the standard deviation was 0.6 pounds. All right, so in this case, we would have our sample size, our sample mean would be the same. But now that standard deviation is for those 6 lobsters. So we're estimating a mean, but sigma, population standard deviation unknown. And that's how we know to do a T-interval. All right, so those are our 2 cases of estimating an unknown population mean.